Okay, guys, it's time to, now that we know all about exponents, to enlarge our repertoire of functions. We've talked about linear functions. We've talked about parabolas, y equals x squared. We've talked about absolute value functions. But today, instead of looking at y equals x squared, which was our basic parabola, I'm going to switch the roles here and look at not x to the 2, but 2 to the x. Now, we've never had that situation before where our variable is up there in the exponent. So let's just make a table of values and then plot some points and see if we can figure out what this looks like. So I'm going to let x be 0 and 1 and 2 and 3 and -1 and -2 and -3. So we'll take turns. Jackson, if you put a 0 in there for x, you get 2 to the 0, and that's what?
1.
All right. No matter what you have, anything to the 0 power is 1. Becca, if you put 1 in there for x, you got 2 to the 1.
That's 2.
Isaac, if you put 2 in there for x, you have 2 squared.
It's 4.
Jackson, if you put 3 in there for x, you have 2 cubed.
8.
Becca, if you put -1 in there for x, you have 2 to the -1.
1/2.
2 to the -1 is 1 over 2 to the 1. So you're right, it's 1/2. And if you put in -2, Isaac, 2 to the -2.
Would be 1/4.
That's right. 1/4. And Jackson, 2 to the -3.
1/8.
Good. So I'm going to draw the graph. 0, 1 is our y-intercept. When x is 1, y is 2. When x is 2, y is 4, which would be about here. When x is 3, y would be 8, which would be about there. When x is -1, y is 1/2. -2 gives us 1/4. -3 gives us 1/8. So this is really a brand new kind of a function. And the graph looks something like that. Okay? And it is one of the most important functions that we study because it's an example of what we call exponential growth. Exponential growth. And something can grow exponentially for a long time and you hardly notice any growth at all. Look how slowly it's rising. But then it always kind of turns a corner and then all of a sudden it just blows up on you. Everything in the world, it seems like, is growing exponentially. Some good, some bad. Population of the world is growing exponentially. The amount of pollution that we dump into the atmosphere is growing exponentially. But if you put money in the bank, it also grows exponentially. If you don't have very much money, it seems to grow very slowly. But if you have a lot of money, it grows very quickly. Okay? So this is our first example of an exponential function. Now we use 2 here, so this would be called the exponential function base 2. Okay? Now if I did y equals 3 to the x instead of 2 to the x, we would get generally the same shape. 3 to the 0 is still 1, so it would still go through that same y-intercept, but 3 to the 1 is 3, and 3 squared is 9, so it would grow even faster, okay? But it would have that same y-intercept. Another important characteristic is, notice that if you just let x be more and more negative, you would get a smaller and smaller fraction, but it would never equal 0. So if I look out way out here to the left, it just keeps getting closer and closer and closer to 0, but it never reaches 0. It's what we call a horizontal asymptote. It just gets closer and closer to that line, but never touches it. So y equals 2 to the x, y equals 3 to the x, y equals 10 to the x. All these graphs have similar shapes of exponential growth. It's just that some of them grow faster than the others. They all have a y-intercept of 0, 1, because anything to the 0 power, no matter if it's 2 or 3 or 10, anything to the 0 power is 1. Now, as a third example, let's look at the function y equals 1/2 to the x. So that would be called the exponential function base 1/2. And let's do the same thing. Let's put in 0 and 1 and 2 and 3 and -1 and -2 and -3. So we'll go left to right this time. Isaac, 1/2 to the 0.
1.
Right. Becca, 1/2 to the 1.
1/2.
Jackson, 1/2 squared.
1/4.
Yep. Isaac, 1/2 cubed.
That would be 1/8.
Very good. Now, Becky, you got the hard one. 1/2 to the -1 power.
That'd be 2.
Very good. There's many ways you could look at this. You could say it's 1 over 1/2 to the 1. So that's 1 divided by 1/2. But again, the way we divide fractions is we multiply by the reciprocal. Dividing by 1/2 is the same as multiplying by 2. So you're right. This one is 2, and this one is 4, and this one is 8. Okay? 1/2 to the -3 is 1 over 1/2 cubed. So it's 1 divided by 1/8, which is 8. Okay? So when we look at the graph, zero, 1, we've got our same y-intercept, but 1 1/2, 2 1/4, 3 1/8. This horizontal asymptote that I mentioned before is out here to the right this time. -1 2, -2 4, -3 8, and so forth. So our graph this time is what we call exponential decay. Something is dying off exponentially. And I think in a previous lesson we talked about radioactive substances decay exponentially and exhibit this kind of behavior. Now, if I did 1/3 to the x, if I did 0.1 to the x, if my base was less than 1 instead of bigger than 1, like our first two examples, I'll get exponential decay. All right? So to summarize what we know about exponential functions so far, we can say this. If you have y equals b to the x, no matter what positive number b is, your graph will be an exponential function, and if b is bigger than 1, like 2 or 3 or 10 or whatever, it'll be exponential growth. But if b is less than 1, like 1/2 or 1/3 or 0.1, then it'll be exponential decay. But in any case, the y-intercept is 0, 1. Okay? Now, we don't always want the y-intercept to be 0, 1. So what we do to this function typically is we multiply it by something. If we had y equals 3 times 2 to the x, a times b to the x, think what the y-intercept would now be. Put 0 into that function, and what do you get? 3. Because 2 to the 0 is 1, and 3 times 1 is 3. So now, when x is 0, y is 3. Okay? What about when x is 1? Jackson?
6.
What about when x is 2? Isaac?
12.
What about when x is 3? Becca?
24.
And I want you to notice something. When we were talking about linear functions, remember how we always used to say, it's growing by the same amount each time. This is growing by 1, but to get from 3 to 6, to get from 6 to 12, to get from 12 to 24, you don't keep adding the same thing. You keep doing what, Isaac? Multiplying. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24, and so forth. So you can recognize exponential functions if you just take a look at the pattern here, and if you're multiplying by something each time instead of adding the same thing each time, that's an exponential function. So I hadn't anticipated doing this, but I just got to. If I give you some points like 0, 4, 1, 12, 2, 36, 3, 108, I'll bet you can tell me the formula for this function. It's not going to be linear, it's going to be exponential. So it's going to kind of look like this one, isn't it? It's going to be some number times some number to the x power. Jackson.
4 times 3.
Yes. The y-intercept is 4, so that's the number out in front. We are multiplying by 3 each time, so it's 3 to the x power. Perfect. Get the idea there? All right. Now, in an earlier lesson, we talked about the fact that calculators handle exponents very well. So suppose I define a function to you, and I say our function is 10 times 1.2 to the x power. Now already you know one or two things about this function. Tell me one thing you know right off the bat. Jackson.
The y-intercept is 10.
The y-intercept is 10. So it crosses the y-axis at 10. And Becca, what else do you know about this function?
It's exponential.
Exponential what, though? Growth or decay?
Growth.
Growth because the base is bigger than 1. As soon as the base is bigger than 1, you know you have exponential growth. Now, we're not sure if it's growing that fast or growing that fast or growing that fast. Okay? It all depends on how much bigger than 1 that number is. Okay? But if it's got a 10 out in front, that's our y-intercept. And if the base is bigger than 1, it's got to be growing relatively quickly. Okay, so let's find another point on this graph. Let's let x be 3. Let's put 3 into this function machine like we talked about in a previous lesson. I want to come over here to 3 and find the y-coordinate of my point. So I need to calculate f of 3, and just like for any function, that just means you need to put 3 in for x. So the 10 is going to stay 10, the 1.2 is going to stay 1.2, but now x is 3 because I'm calculating f of 3. Well, there's no way I'd want you to do that by hand. You could do it. You could take 1.2 times 1.2, get that answer, then multiply by 1.2 again, get that answer, then multiply by 10. I'm not going to ever ask you to do something like that because you've got a calculator. All I'm going to do is come to my calculator and say 10 times 1.2 to the power 3. Okay? And when I hit enter, it's 17.28. Okay? The y-intercept was 10, but when x is 3, we're up to 17.28 with our y-coordinate. Okay? So I could give you any number whatsoever if you have your calculator handy, and you could plug it into this function and find the y-coordinate. Okay? let's do one more example. Suppose I have f of x is 100 times 0.2 to the x. Isaac, what's one thing you know about that function?
It's having exponential decay.
Exponential decay, because this time our base is less than 1. And Jackson, the other thing we know is
The y-intercept is 100.
the y-intercept is 100. So this function is looking like this, isn't it? And this is the point 0, 100. Okay? But if I come out here to this point, whose x-coordinate is 10, I wonder what the y-coordinate is. Well, all I have to do is stick 10 into the formula. I need to calculate f of 10. X is 10. So this x is 10. And that's where the calculator comes in. I'll just take 100 times, and then it's 0.2 to the 10th power. And look how quickly that thing has decayed. 10th, 100,000th, 10,000th, 100,000th. The y-coordinate of this point is already so close to 0 that you can hardly see it at all. It's only 100,000th. This is the point 10, comma, 10th, 100,000, 10,000, 100,000. Okay, we knew it was going to be small because it was exponential decay, but see, this number is so much less than 1 that it's really dying off quickly. If we had a 0.9 here, which is closer to 1, it would still die off, but not as quickly. So that's basically it. If you have a times b to the x, a tells you the starting point, it tells you the y-intercept. B tells you if it's growing or decaying, depending on if it's bigger than 1 or less than 1. And the further away from 1 it is, the faster it grows or the faster it decays. Okay? So that's our introduction to exponential functions, which I consider to be probably the most important functions we study, because everything in the world seems to be growing or dying off exponentially.